Okay, so what I want to do today is hopefully kind of tie together a lot of the things that we've been talking about regarding internal energy and enthalpy. Just kind of put them into context for a second. I've already done a lot of talking about the different forces that result in energy storage and transfer, and so now I just want to give some specific examples of processes that result in change in enthalpy and try to trace those enthalpy changes back to the actual forces between the molecules. So hopefully we'll be able to do that. We're also going to just take one more step forward, utilizing the fact that enthalpy is a state function to be able to determine reaction enthalpies for uncharacterized reactions based on characterized reactions. We'll take a look at that. After that happens, hopefully, if we still have some time on the clock, we're going to do a problem. There's a problem in the homework that might need a little bit of explaining, so we'll discuss that problem. And then if I still have time, we're going to go back to ideal gases and look at energy changes associated with expansions and contractions under different conditions. So first to wrap up, enthalpy, just to review real quick, that enthalpy function is useful because it keeps track of all of the energy changes that are associated with a process at constant pressure. And again, a process at constant pressure is the kind of process where not only can the internal energy of the system change, not only can energy enter the system as internal energy or leave the system as internal energy, but energy can also enter the system or leave the system as work done by expansion or contraction. And so if the system is expanding, it's expending energy as work, pushing back the atmospheric pressures. If it's contracting, work is being done on it as the atmospheric pressures push against it. And so enthalpy function is an inherently more useful function than the internal energy function, simply because it tells us how much energy to expect to flow, that we would expect to flow between two systems in the course of a process that happens under constant pressure, right? Which the majority of the reactions that we carry out in the lab are these reactions that happen at constant pressure. So remember, it's the enthalpy term is composed of an internal energy term U and a PV term. The U term itemizes all of the internal energy exchanges, the changes in internal energy, and that PV term kind of accounts for the work, the expansion and contraction work that is done at constant pressure. And the heat that is evolved under constant pressure conditions is equal to delta H. We did a little derivation for that last week. So, so low tech. So just again, you want to be thinking of that constant pressure heat QP as being the energy flow, the net energy flow that happens with that process that happens at constant pressure. We've got several different kind of scenarios that we can watch heat flow in a constant pressure process. One of those is heating. So you can heat a solid, you can heat a liquid, you can heat a gas. In all of those cases, a couple things will be happening. As energy is dumped into a system as heat, you can excite the internal modes of the system. So if it's a solid, we said that solids have those bulk vibrational modes. If you raise the temperature high enough, you can excite electrons in a solid as well. And so heating leads to those excitations of the vibrational modes. It can lead to excitations of electrons. You don't have so much in a solid the vibrations of the individual atoms contributing. There's the whole system kind of vibrates together. So the individual atoms and the molecules, you don't have to worry about their vibrations as much. But you do have to worry about bulk vibrations, and you do have to worry about electronic excitations. These are all things that can happen in a solid as it's heated. So energy can be put into there. The other factor is that when you heat something, it expands. A lot of things expand or contract with heat, a lot of things expand with heat. And so if it's expanding, it's pushing back those atmospheric gases, and it's doing work on the environment, and so there's energy spent in expansion. So whenever you see an equation like this, all of our solids and liquids and gases will come with their own specified heat capacity. Putting that with M there specifies that it's a molar heat capacity, so then you have to multiply the molar heat capacity by the number of moles, by the change in temperature, and that will tell you how much energy has flowed into or out of the system for that particular phase transition, or for that particular heating cycle. Liquid phase, you still got the vibrations. You've got the bulk vibrations of the solid kind of turn into bulk vibrations of the liquid, but also you end up with individual vibrations of individual molecules. You end up with electronic excitations. We talked about rotations. Rotations aren't as important in a liquid phase or a solid phase because the molecules are kind of locked into position by their frictional forces or their intermolecular forces. But you do have the vibrations of the individual molecules. And again, you heat it up high enough, you can get electronic excitations in a liquid. Your gas phase, you start heating something in the gas phase, your vibrations get excited of individual molecules. You get rotations now that come into play. Molecules can store energy in their rotational motions in the gas phase. Again, there's always translational energy. I should have mentioned there's translational energy in the liquid as well. And in the gas phase, if you heat it high enough, you can get those high energy electron excitations. And so when we talk about heat capacities for solids and liquids and gases, we're kind of incorporating all of these modes of storage, all those modes of energy storage. So, and also in addition to these, those modes of storage, again, anytime the system is expanding or contracting, there can be energy spent as work, expansion work. So that applies to all of those, the solids, the liquids, and the gases. I know that I'm being a little redundant with the subject of forces. I'm doing that because honestly I think it's the best thing for you guys as chemists is to be able to try to watch any process and think of it in terms of the exact intermolecular forces that are involved. So I know that we talked about this before, but I just want to make sure that it's down pat before I move on to those things. Phase changes. You've got several different kinds of phase changes. There's many different states of matter. And anytime you move from one state to another state of matter, you're going through some kind of a phase change. You can have a solid phase moving into another solid phase. You can have a solid phase moving into a liquid phase. You can have one liquid phase transform into another liquid phase. We think most frequently of phase changes in terms of solid transitioning to liquid, liquid transitioning to gas. Those are the easy ones. But we did mention that when you have a situation where a molecule moves from one specific electronic environment and into another one, for instance, the dissolving of an ionic solid into water, that's a change in phase. It's moving from one phase to another, and the two phases will have differing intermolecular interactions. And so, I guess take-home message for phase changes is when we're putting energy into a system and driving a phase change, what we're really doing is we're acting to alter the intermolecular interactions. So in solid phase, you've got things that are bound very tightly, and well, let me get to the next slide before we have this conversation. Real quickly, mathematically, the form that the calculation for a phase change comes in ends up not involving the heat capacity. There will be a defined molar enthalpy of transition for that particular transition. So you guys know that there's a defined amount of energy that is required to move water from the liquid to gas state. Well, that's the enthalpy of that transition. So if you want to calculate the heat or the energy associated with the phase change, you're going to multiply the number of moles undergoing that phase change by that standard transition enthalpy. In addition to the energy that is required to overcome intermolecular forces for a phase change, if that phase change results in a change in volume, again, you've got expansion and contraction work. And so any phase change that's accompanied by a change in volume, there's also going to be an energy change associated with any work done onto or by the surroundings. one at a time real quickly. So in melting, in freezing, you're going from the solid to the liquid phase. The opposite is moving from the liquid phase to the solid phase. So fusion is melting, freezing is going from liquid to solid. And the biggest chunk of the energy involved in those transitions are the energies associated with separating the molecules away from their intermolecular forces. So water is held together by those hydrogen bonds and those electrostatic interactions. If we want to take water from the solid phase, ice, and drive it into the liquid phase, we're going to have to put in enough heat energy, enough enthalpy to overcome those intermolecular attractions. And also, if there's a volume change, you've got work associated with that as well. So your enthalpy fusion is going to be the number of moles times the specified enthalpy of that transition or that particular fusion transition. The opposite direction, you can just flip the sign on this. Vaporization, basically the same thing. If you're going from liquid to gas, the energy that you're sticking into that is the energy that's required to, for instance, in the vaporization of water, is to push those, the energy required to push those water molecules apart against their intermolecular attractions. So that's the bulk of the energy associated with that, that phase change from water. But in addition to the energy required to separate them from their intermolecular attractions, there's also, at constant pressure, going to be some work done as the gas expands against its environment, right? And so you'll have in that vaporization condensation phase change, you'll have a chunk of energy that is expended as the gas expands against the external pressure of the environment. Now, ionization. And I don't know if are you guys reading the book? I recommend you read the book, because a lot of the things that I'm talking about are stated in similar ways, with a little twist in the text, and so cross-reference everything I say with what you read in the text. Ionization enthalpies. So there's a certain amount of heat that is required to take a substance and move it from one ionic state to another, or move it from a state that doesn't have a charge to a state that does have a charge, etc. And while there may be some small volume change associated with ionizing something or heating it up, there might be a volume change associated with that. The bulk of the energy, the bulk of the enthalpy associated with ionization is simply that energy required to separate a positive charge from a negative charge, or bring two negative charges together, against their electrostatic forces. So your book gives some examples of these. You take magnesium and you pull off one of the electrons by heating it up, getting it to pop off, and it's going to require 738 kilojoules per mole. So there's going to have to be an energy investment in order to separate that ion from the attraction to the nucleus. That second equation, we're taking the already formed Mg1 plus ion and we're turning it into the Mg2 plus ion. And same thing, it's the energy associated with pulling that electron away from the nucleus. At this time, the ionization energy is 1,451 kilojoules per mole. Why is it so much higher the second time around than it was the first time?
Attractive force between the nucleus and the electron is much more, because it's much closer to the nucleus.
Yeah, you got, now, when the first one that you did, you had a neutrally charged species, and there was some attractive force between the nucleus and the electron. After you popped that first electron off, the effective charge of that nucleus became greater, and so the pull that it exerted on your electron became stronger. And so the force that you needed to remove that electron, the energy that you needed to put in to move that electron became larger. So generally, the second ionization energy is always larger than the first ionization energy. Right? Some species end up forming positive ions. We know that other species form negative ions, and those negative ions are due to the attractive forces between the atom and the electron. Chlorine is a good example of this. You notice that when you add that electron to the chlorine, you end up releasing 350 kilojoules per mole. So Again, this is all electrostatics. Go ahead.
Should that be, for chlorine, should that be ionization energy or electron affinity? Because you're adding electrons to it.
I just call it ionization because your book defines it differently. I use whatever language I like to use, but they call it electron gain enthalpy, electron affinity. The electron affinity is the relative force that it attracts the electron with. The energy, that would be referred to as an enthalpy or something like that. But yeah, we could call it the electron gain enthalpy. But whatever, however you look at it, the energy that's associated with it is the release of the electromagnetic field energy when that negative electron is pulled in towards chlorine's nucleus, right? So that's all it is. Chemistry is really simple once you break it down to just the forces. Problem is you get the language that gets difficult and everybody thinks chemistry is ridiculously hard, but chemistry is not that hard. It's just logic. Got something like oxygen, you want to form the O2 minus ion. If you've already formed the O minus ion, it's going to cost you energy to shove that other electron onto the oxygen against the repulsive charge of the already negatively charged atom, right? And so trying to stick an electron onto an O minus to form an O2 minus ends up costing you. You got to spend 844, almost 1,000 kilojoules of energy to do that, right? And our biggest issue, the scenario that we encounter most frequently are the enthalpies associated with chemical reactions. And this discussion is highly analogous to the ionization discussion. We're just talking about energy that is that's associated with the movement of those electrons away from and then towards an atom. So if you want to break a bond, you're going to have to spend energy to break a bond. There'll be some net energy expenditure to pull an electron away from whatever atom it's associated with. And if you want to allow that electron to make a new bond, there'll be some net energy gain when the electron is allowed to approach the new atom or form a new bond. And the bulk of the energy associated with a chemical reaction is going to be the differences in the energy of the bonds that are broken and the bonds that are formed. If the bonds that are broken are stronger than the bonds that are formed, the reaction will require an input of energy. If the bonds that are broken are weaker than the bonds that are formed, the reaction will result in a release of energy. There will also be, in any chemical reaction, probably some change in volume. And if there's a change in volume, there'll be some work done in expansion or contraction against the internal forces, right? Or against the external forces of the environment. And so it's all electronics, right? All of these enthalpies, it's just a result of electronic interactions, either electronic interactions between two molecules or electronic interactions between one atom and an electron and another atom and an electron. And then whatever that expansion and contraction work is. For our chemical reactions, we've learned to calculate delta H by using the formation enthalpies of different compounds. And so our formation enthalpies were defined to be the enthalpy that was required to form a compound from its elemental precursors. We would like to be able to just take the enthalpy of the products and subtract it from the enthalpy of the reactants, but it's the absolute enthalpies. But it's difficult to know absolute enthalpies again because it's a function of the internal energy and the pressure volume term, and there's just so many things in there that it's a rough calculation to make. And so to skip that, we use these formation enthalpies where we kind of define a zero and movement in between those is just kind of relative to the energies of the elemental precursors. Did I say that right? So we use formation enthalpies. And that's great because the formation enthalpies allow us to not have to know the absolute enthalpies of our products and reactants, which are difficult to calculate. But there is a little, there's some problems sometimes with formation enthalpies, and that is that some of them are very difficult to calculate because of experimental complications. So what we want, ideally, is to have a big table in the back of a book that has the formation enthalpies of every compound we could ever imagine needing to use as a product or reactant. If we have every compound that we could ever make or destroy in our chemical reaction, then all we have to do to calculate the enthalpy of that reaction is subtract enthalpy of the products from enthalpy of the reactants, and we got it covered. But here's the problem. Let's say we want to calculate a formation enthalpy for ethane. Ethane, right? Ethane's 2 carbons. Who's had organic chemistry recently? So we want to calculate the formation enthalpy for ethane. Theoretically, all we would have to do is throw a couple moles of graphite and 3 moles of hydrogen gas into a constant pressure calorimeter. It's a calorimeter with the lid removed so it's exposed to atmospheric pressures. Run the reaction, figure out how much heat moves in or out, and we're done. As long as the reaction has gone to completion, and then we can attribute all of that heat to the chemical reaction that took place. But if you take graphite and hydrogen gas and you throw them into a constant pressure calorimeter together, they're not going to go on to form all ethane. There'll be multiple intermediates that get formed. There might be side reactions that get formed. And so if you measure the heat that comes off of this reaction and you try to attribute that heat to the formation enthalpy of ethane, you just made a really big mistake, because not all of that heat was associated with ethane formation. The reaction probably didn't go to completion. And so the question becomes, how can we calculate formation enthalpies by using the fact that enthalpy is a state function and using known enthalpies of reactions that do go to completion? And this is what I'm going to try to illustrate next. So state functions are cool because anything that we want to calculate, or we're free to calculate along any path we choose. We don't have to calculate changes in enthalpy along a path that leads straight from reactants to products. We can go through intermediate paths. That's the fact that we employed when we decided to use formation enthalpies. In the case of formation enthalpies, we're saying, okay, let's go from reactants to precursors and then to products, instead of going from reactants straight to products. Well, there's another way to, there's another kind of employment of that state function quality that allows us to calculate formation enthalpies from other reactions that are characterizable. So if it turns out that combustion reactions, recombining something with oxygen, these reactions are very vigorous reactions. They happen very quickly, and they go almost to completion, right? You light a match on fire, and the thing poofs, and all the carbon gets turned into carbon dioxide, but if you run it hot enough, long enough, it does go completely carbon dioxide. You'll notice that with just 3 simple combustion reactions, we can end up recombining the reactions into a net reaction that sums to the reaction that we were originally interested in. We originally wanted to know what is the formation enthalpy of ethane. If we take some ethane and we combust it, right? Blow it up, turn it into carbon dioxide and water, we can calculate the delta H of that reaction. And we'll be fairly certain that that is in fact the delta H that we're looking for, because the combustion reactions go to completion. Side reactions are kind of minimized. We can take some graphite, we can combust it and turn it into carbon dioxide, right? Take the graphite, throw some oxygen in there, torch it, measure the heat. Now we've measured the delta H for this reaction. Similarly, we can take hydrogen, throw it in with some oxygen, run the combustion reaction, and figure out delta H of this reaction. So if we take reaction number 2, write it in the forward direction 2 times, and then take reaction number 1 and write it in the reverse direction, assign a negative to the delta H of 1, and then take 3 times reaction number 3 in the forward direction, and then sum those together, you'll notice that the net is our reaction of interest, formation of ethane, and the total delta H of this reaction is just going to be 2 times the delta H of reaction 2 minus 1 times the delta H of reaction 1 plus 3 times the delta H of reaction 3. So we can take reactions that we know the enthalpy for and recombine them in a path that regenerates our reaction of interest, sum the enthalpy changes, and we're done. That is why when someone says enthalpy is a state function and they act like they just said something really important, they did say something really important. Because it was the fact that enthalpy was a state function that allowed us to calculate all of those different enthalpies that we have itemized in the tables in our texts. Right? So it's very important that enthalpy was a state function. If it wasn't a state function, we'd be up a creek. We wouldn't have all this information, this wonderful information that we have about energetics of reactions. Let's look at problem number 11. Number 11 is it's the ability to solve problem number 11 is a result of enthalpy being a state function. And looking at problem number 11 is going to teach us to associate enthalpy changes with the bond enthalpies and the phase change enthalpies of any kind of a reaction. Remember, energy is it's additive. One energy change plus another energy change ends up being the total energy change of the reaction. So they tell you that the formation enthalpy of cyclopropane is 53.3 kilojoules per mole. So that means that when cyclopropane is formed from its elemental precursors, 53.3 kilojoules of energy are released, right? They ask you to use that value to calculate the carbon-carbon bond enthalpy for cyclopropane. And they're going to give you a few things. They're going to tell you that the standard hydrogen-hydrogen bond enthalpy and the standard carbon-hydrogen bond enthalpies are 436 and 413 kilojoules per mole respectively. And they tell you that the delta H of sublimation for graphite is 717 kilojoules per mole. Right? Why do you? What are they asking you to do right now? We got a reaction. Let's draw out the reaction. We've got cyclopropane. So we got what? 3 carbons, 6 hydrogens. So we've got 3 H2 in the gas phase plus 3 times carbon in graphite plus 3 times carbon in graphite phase, going on to form C3H6, which is actually a cyclic structure. Looks